Okay, thank you. Thank you for the invitation. The talk I'm going to give today is going to be a methodology talk. In particular, I'll be speaking about computer-assisted experimental method. And as you can see here, this is based on a paper recently published in Management Science, just came out, as you can see. And Dan Cavagnaro, he's first author. This is primarily his work. He made all the slides, so I just borrowed his. And as some of you may know, Dan is a former graduate student of this program, IMBS. And after his degree, he spent a year at Illinois with Mike Regenweder, and then came to my lab for postdoctoral work. And by then, Mark Pitt, his colleague of mine at Ohio State, we developed this computer-based experimental methodology, and Dan thought that wouldn't be cool to apply this to judgment decision-making. That was his domain that he was familiar with, and that is the one result. So just a preamble, and I'm not a JDM person by training, so if you have any questions deep enough so I can answer, I'll just refer to him. Okay, so if I were to give a one-page snapshot of this entire one-hour talk, and this would be images, wordle images. So it's about experimental. So if you're going to conduct the experiment, purpose is discriminate formal models, so mathematical models, and you want to design the experiment in such a way that will optimally or maximally discriminate your formal model. It could be 2 models or 3 models, 4 models. And I'm taking Bayesian approaches. Whole thing is couched in a Bayesian decision theoretic framework. As you can see, also adaptive, meaning that while you conduct an experiment, you keep fine-tuning your design. So what stimulus values, the treatment level you present from one trial to another trials. So there's an optimization. Computation is very heavy computation. And so that's what I'm going to talk about. This particular talk today is one application to judgment decision making. We have applied this method to other domains like visual psychophysics, retention memory, developmental psychology, and this and so. So whenever we have new postdocs say, what's in the areas? You have developmental psychology, maybe you should be applying this to your areas. So that's what we've been doing. So just want to start out with this outline. I'm going to have a few minutes talking about the introductions and then the background, in particular what we call Marshall and Machina triangle. And then that is the main section. So data collection or experimentations. So this is the name that we start calling adaptive design optimization. ADO is essentially adaptive experimental tool. And then example application, this to JDM. And this particular application example will be all computer simulations, though we have applied this to actual experiments. That's another paper. So here's a choice experiment you might want to run. So here's a gamble A and B. And so in these 2 gambles, the amount of money you win, that's all fixed. $1, low and medium and high, same for the gamble B. But what's different between 2 gambles? The probabilities. So gamble A has 75% and to win $1, and then there's 20%, so there's a 2 extreme here between, and then low and high value. And then gamble B has different probability distributions on this. So typical gamble experiments. So question is, how do you choose? And one idea would be perhaps maybe we maximize expected utility. So this is how you compute the expected utility. So for you multiply this probability by utility of this, the dollar value one, and then choose the one that has higher expected utility values. And if you were to assume linear functions, so the identity utility function, just for the moment, and then the gamble A has a higher value, what we expect utility, and then you may want to choose the gamble A for that one. But it's been shown numerous times for many years that people's choice behavior violate expected utility. And so there's a plethora of different alternative models and theories being proposed. And here's some of those examples. So instead of expected utility, maybe there's a weighted expected utility or nonlinear or rank dependent, and so on and so forth, even more. The prospect theory, regress theories, and then there's the models theory called text, which is Michael Birnbaum's ideas, and so on and so forth. So suppose that you want, for example, want to design an experiment that could decisively distinguish between these different models of theories. Suppose that's the goal of your experiment. So there's so many of those. And so the typical way of you would do this experiment is that this flow chart, so you formulate your models and collect the data and analyze the data. So the formulate model in terms of axioms, what's the stochastic, the behavior you want to capture, is expected utility or weighted expected utility, prospect theory, or text. You formulate those. And then you run the experiments to collect the data. And the idea is that you want to collect a large amount of data, a lot more subjects. You want to decrease the noise. And then once they have data, you fit your models to your data. And since you might have multiple models, you could apply maybe model selection criteria. Things like that has been done numerous times, and there's been no clear winner, one way or another. So what we're going to propose today, so this is a new approach to data collection, is that we're going to be focusing on this second middle step, collection, data collection step, or experimental step. Instead of you design what kind of gamble choices or pairs of gamble you want to present, we're going to adaptively adjust based on the choices from one trial to another choice. Idea is that you want to collect the smarter data in such a way that you want to highlight the difference between the models from one to another. So just give a very quick one-shot example. So this is not a JDM example. Suppose that you're interested in discriminating between, say, two models of retention memory. So we have a power model. So this is the time, the retention time, and this is a proportion crack. And here's a power curve under a certain narrow range of primary values. So this is a typical power curve. You can generate it, and exponential have these. Suppose that these are all possibility that power is an exponential model can generate. And obviously in this case, to discriminate between these two, and you know what they pick retention interval. It should be like a 5 second, 10 second. In this particular case, obviously you do not want to choose the value 10 or above, because these range of here, these two models make virtually identical predictions. So most distinguishing region will be somewhere between 0 and 5, because this is where that power and exponential make differential prediction. So that's the ideas. But the problem is that in reality, and the parameter values is unknown, is because if you vary the entire parameter values, it will completely fill up this region. So it's not visually clear cut. So that's just what you're going to use a computer. So that's basically what we're going to do. And so what I'm going to propose is called adaptive design optimizations, ADO. So it's adaptives. So the idea is that instead of one-shot sort of serial from the formulate models and data collection, analyze it, that's the traditional typical approaches. What we're going to do is that it's going to be circled around these two. So that on each trial, we will pick stimulus values that has best chance of discriminating the models of your interest. Okay? And then you present that to the subject, and you collect the data, which is like choices. It's a gamble A or B and B. And then you analyze the data, and they will provide information about which model maybe you're leaning toward one model versus another. Based on that, you pick another optimal pairs of gambles, right? And you just rotate around this, okay? So online in real time. So that's what I mean by adaptive, means that this sort of sequence of the gamble pairs you're going to present is not predetermined. It will be dictated by your models and participants' choices. So that's basic ideas. So But particular design that we're going to be talking about today is just one of the simplest ones. So I'm going to spend some time talking about this, what I call the triangle. So let's suppose that every gamble you're going to present in this setting is basically 3 outcome gamble. So that this is the low and medium and high, and assume that in this target list, those outcomes are fixed. So it could be like $1 or $50 or $100. So we're going to call low and medium high. What you vary for each gamble, that's a probability. Probability of winning low outcome, medium, and high. So these 3 probabilities, so that every gamble, you vary these values, right? Of course, because this probability must be something equal to 1, okay? So that's the constraint. So under that, because of this, the normalizing constant, so that every possible gamble, one particular gamble, which you vary this, the probability value, low, medium, high, can be represented on this 2-dimensional triangle like that. So that is the probability high. So it can go from the 0 to 1. And so along these axes, probability of low is always a 0. So that either you get the probability of high outcome, say 0.5 over here. On this axis, probability of high would be 0. And then, so any possible, for example, so this is actually called triangle. So for example, so if you're going to present particular gamble, which is this distribution, 0.3 for low outcome and 0.4, that would be 1 point over here, okay? And then at that point will be corresponding to that the probability of getting high outcome will be 1.0, everything else will be 0. So that every gamble could be 1 point on this triangle. So now suppose that you want to design an experiment to distinguish different utility theories, for example. And then in a paper by Colin Cameron in 1989, basically has shown that on this 3 outcome gamble, where that the values were fixed, and so you can only vary the probability, it can be shown that what you call the indifference curve, you can actually conceptualize in such a way that every point here, this is a gamble, so that if you connect all these gamble pair that give you exactly the same expected utility, and this is called indifference curve, right? So that means every gamble on this, they are has equal utility value under expected utility or weighted utility, so whatever.
And
that
U is an unspecified function.
Which has to be specified, okay. So for example, simplest one, expected utility, and it has basically, he has shown that, so that those indifferences curve is going to be parallel straight line, okay.
So
and
what was that wiggly line?
Oh, that's a,
results?
or that is almost arbitrary. Not even prospect theory can predict that. I have example for rank. So that's an arbitrary case. I don't think we have any theory can actually predict that. That's a highly nonlinear. So simplest one, expected utility will predict that one. So that if you had a gamble here, one over here, they have equal utility value. But what a gamble, one here, another pair here, then a current expected utility, this must be preferred over that one.
So
right?
All you need is that U is smooth. If you take the first derivative, then you're just using the inverse function theorem. That's what it is.
That's absolutely it. And just make sure. So that's what the EU predict. Of course, that different utility functions or different nonlinear function will give you different slope. Okay, that's the only thing is vary. Okay, but it has to be parallel line, right? On the other hand, there's a extension of expected utility called weighted expected utility, and which actually assume another additional parameter that a certain outcome it give additional weight, higher or lower weight. So additional weighting, the multiplicative weighting giving. So they have another extra parameters. It turns out the currently calling camera that will give you not the parallel but the straight line, but it will have sort of meet one point, sort of fan in or fan out patterns. So particularly in this case is if the median value get lower weight than the low and high, and that will have this fan out pattern just like that. So you can see that those two theory, expect utility, weighted one, it make qualitative different prediction patterns of indifferences curves, okay? Regardless of what actual utility function, as long as you confirm this either EU or WEU. Right? So these are qualitative predictions that made by each of these theories. Okay. And then here's the rank dependent. So it turns out to rank dependent expect utility, it actually makes curved prediction. Indifference curve is not going to be a straight line. And in particular, it turns out that that's intersect on this hypertenuse, this line here. So these are sort of qualitative prediction. Of course, different prospect theory and tax will have different sort of indifference curves. Okay. So just pretend that for now, suppose you're interested in discriminating between, say, EU versus WEU. So the EU make a parallel prediction, WEU make, say, fan-out patterns. Okay. So you want to design the experiment such a way that you want to discriminate these two models as quickly as possible with the minimum number of experimental trials. And the one method you can use is what I call the adaptive design optimization method. Okay, just before I talk about that, just give you a bit more motivation. So again, we have here MM triangle, and here's a one gamble, A1, and gamble B1, all right? And then in this case, the expect utility, for example, if this is particular expect utility, indifference curve, according to the EU, because this A1 gamble will have a higher expect utility value, so that you would prefer A1 over B1, right? In this particular EU. And this is another EU, but different utility function, but still EU, still the parallel line, and still A1 should be preferred, right? And still A1, okay? Now, here's another EU, but different utility function. In this case, for example, now, then B1 should be preferred, right? So even though same EU, depending upon particular utility function using, it makes different predictions. On the one, say A1 should be preferred, the other one, B1 to be preferred, right? The same, right? All right, so that means that when you actually present this particular gamble pair, and you assume that underlying behavior captured by EU, and if you observe that A1 is preferred, then you can say that particular utility indifference curve should be something like that, okay? On the other hand, it's a B1, and then curve will be much lower slope, okay? So that's how you can sort of make quality different predictions, even on the EU, all right? So now, in reality, actually, you present the multiple pairs. So suppose that you have 4 pairs, and then A1, B1, A2, B2, and then this is what you observe, for example. And between an A1 and B1 was subject towards B1 over A1. And A2 and B2 was A2, for example. So if this is particular choice pattern you observe, and you try to see whether this EU can actually predict this particular choice pattern among 4 gamble pairs, right? Well, there's a 1, for example. So if the EU has these indifferences curve that can fully consistent with this particular pattern of choice behavior among 4 gambles. Well, I think that there's also weighted EU can also explain the same choice pattern. So this is a case where that if you're going to present these 4 pairs, they're not discriminative enough, because that there's a EU model that can predict this pattern, there's a WU model that can predict this pattern, right? So idea is that is there any way we can actually come up with sort of pairs of gambles, the kinds of gamble pair that can actually discriminate between these two, EU versus WEU. And there is one, because here's again typical pattern of weighted EU versus standard EU. And actually, if you present the gamble pair in this corner, this which can see that those 2 models or 2 theories make differential prediction, because this is, but here, not in these regions here. So this is what I call the sweet spot. So you want to choose gamble in that corners, the regions, all right? So for example, if you prepare this A5 for the B5, weighted EU predict that B5 should be preferred, and then same here too. But if you change the gamble pairs, now in this case, this is where that weighted one and EU make different predictions. Say B5 should be preferred, but now A5. So that's the reason, it's a sweet spot, okay? But one issue is that those 2 indifference curve, WEU, WU, under the assumption of particular this indifference curve, because there are practically infinite number of this indifference curve, because the slope can be different for even on the EU, okay? So it's not like there's one indifference curve for WEU, one for expected utility EUs, okay? So there's a parameter uncertainty. We don't know what the actual parameter is, what the actual slope. Even the fan-out pattern, we don't know what kind of fan-out pattern is there, okay? So that parameter value is uncertain, right? So we're looking for the experimental methodology where that, given that you want to discriminate between EU and WEU, where that particular slope, the prime values are uncertain. So you cannot say always give me one corner of sweet spot, depending upon the particular indifference curve and slope. Sweet spot could be different regions, right? So this is where the ADO can come in and can be very helpful and handy. So this is method that we first published results in 2009, and then Carbonaro came in. I think it was like 2010 something, and then he applied these ideas to judgment decision-making domain, and we have a few papers, and we have another paper it's going to come out in Journal of Risk and Uncertainty. So that's the JDM application of ADO. So let's just talk about the adaptive design optimization briefly. So in a sense that ADO works like computerized adaptive testing in psychometrics called CAT, C-A-T. So this CAT has been used for, for example, GRE experiments. So there's not like a predetermined set of the test item. Depending upon how you answer your first item, computer will pick next one for the purpose of estimating parameters, or your ability parameters, or identity parameters, okay? It very much works like that, but our domain of application is not the assessment, but it's a model testing or model discrimination. So ADO is sort of like a CAT, but this is more general purpose computer-assisted experimental methodology for say, psychology experiment. The only thing is that you must have a formal models, right? Because it requires the likelihood functions, and they couch it, as I said, in terms of Bayesian decision theoretic framework. And again, so this is sort of the flow chart, how that ADO works. So you, for example, in this particular JDM application, so that suppose you want to vary this gamble pairs within this MM triangle. So you will search the triangle for most diagnostic gamble pair, given that you want to discriminate between EU and WEU. And then you present that to the subject. Then observe choice, whether the A1 is preferred or B1 and so on. And that will provide information, and then do Bayesian updating, because once you have the observation response, and then you update your Bayesian prior to Bayesian posterior, okay? And that becomes the prior for the next trials. Then you pick what's the now next most informative gamble pair you want to present, and just rotate this around, okay? Until you come to the point where that, according to Bayesian posteriors, the one model is a clear winner than the others, okay? All right. And that's probably the only equation you're going to see. So, so that the underlying mathematical framework works like that. For each design, so this D, it could be vector or matrix. In this case, is our example, the D will be a vector of two elements, because you're only manipulating probability, okay? So that each design, assigns certain sort of the sort of value for each design, and that's what I call expected utility. And remember, this has nothing to do with the expected utility. It's kind of a coincidence. So this is utility of each design, okay? And since we don't know what models actually generate the data, so this is the M is the models. So this is general framework. So suppose you discriminate between M or K different models. And this is a model priors, and model has parameter status of M, and that is the likelihood function, and this is what I call the local utility, because you don't know which model is generating the data. Even the model's parameter is uncertain, okay? So the way that Bayesian handles is that you want to marginalize it. So basically take an expectation over all unknowns weighted by priors. So that is for any potential design that you could choose. and you compute this expect utility. You can see that this is a massive computation you have to do. There's a double integration over data because you have not observed the outcome yet. So you take expectation. And also the parameters uncertain, and also the model uncertain. So this is a massive expectation. Literally, you compute for each potential design, and then pick the one that maximizes this utility values. So that's what you do in each and every trial. Okay. And then this is flow chart because that once you observe the data, and then that provides information about the underlying models, and then parameter values, so that you update, start with the priors, so the parameter priors and model priors, and then you apply this computational algorithm, then pick the one that maximizes utility values, and that will be optimal design. You present it to the participant, and you collect the data, and then with that, you update the prior to posterior, that's a Bayesian updating, and then you repeat this, the posterior become priors, okay? So this sort of Bayesian loop you're just running while you run the experiments. So in the typical investigation, people basically stop here and then and you write a paper. But in this case, just keep rotating until you come to the point where it's that one model has become clear winner, and then you just stop the experiment. That's how it works.
Exactly by experiment in this case.
So that this is where
Collecting a point, or
in this the experiment that the example I'm going to show you is that so which gamble pair you want to present, and that the computer will pick that for you. And then you actually present that to the experimenter, the participant, and that's what that is being done. And then you observe whether that participant chooses gamble A or gamble B.
So that's a full-blown experiment.
Yep, so absolutely, yeah. Okay. So this is called the ADO framework. So the idea is that why we should care about this? Well, if you're going to use, say, intro-psych students, probably you don't need the ADO because there are thousands of them just freely available. But if you conduct developmental psychology experiment, we're using that the infants, they're not hundreds of them, right? And so the limited supply. Or if the fMRI experiment, very expensive, pay like $500 every hour, okay? So if your power analysis show that I need 100 participants, that means easily tens of thousands of dollars. But with the ADO, probably you may not need 100 participants, probably in the 20 or 30, for example. You still get the same quality of data, and that's the idea. Or you do an aging experiment, again, or you actually want to do flight simulator using real pilots. And again, they're not coming unlimited supply, okay? So in those situations, perhaps you can use the ADO, and so that instead of predetermined experimental trials will be adapted to each and every trial, also depend upon particular participant, okay? All right, so that's basically how the ADO works. Now I'm going to talk about some example application to JDM domains, and going back to MM triangles, all right? Maybe this is a point where if there's any questions about the ADO, I can answer. And I sort of try to simplify that mathematical framework and computation, but that actually, this is extremely computation heavy. And most of our time in our postdoc, and they spend trying to speed up. And algorithm way or hardware and software. So we use all kinds of software optimization algorithm, and also all kinds of software, hardware. We use currently graphic processing use GPU. You have to use GPU. And so it's very computation heavy. All right, so well, in this case, let's just say you want to discriminate between those two, EU and WEU, okay? And this method can actually be applied to more than just two models. So they can have actually, in our cases, we had example application of ADO where that we were discriminating 6 different models. It can be done a large number, but of course, computation a lot more intensive. Or it can be actually done with just one models. Your goal is that primary estimations, so that it can be done that way too. It's not necessarily for model discrimination, it can be the primary estimation. Now, of course, that'll be a lot quicker and simpler. And then, but for now, suppose that you want to discriminate between EU and WEU. Again, these are indifference curve. And then expect utility, make parallel. Of course, different values. So this EU have one parameter, which is basically slope. Okay, the different slope means that you have different utility functions. And then the weighted expected utility has this fan-out patterns. Okay, so that this weighted expected utility indifference curve can be characterized by two parameters. So that has we're comparing one parameter model versus two parameters. Okay, and now so this is again MM triangle. So that in this particular application, we simplify this design space. So you're going to pick gambles, sort of discretizes. The only one that sort of residing on this boundary. So that these are, for example, this is one gamble. So this one has the low outcome, 0.1 probability, and 0, and then 0.9. So we discretize it so that number of all possible pairs, so we're going to be presenting in here, just 81, okay, right? Just to simplify it. And so we're going to have two conditions. These are computer simulations, so that we're going to pick this gamble pair among this 81, and according to ADO. And then as a control trials, we're going to have random. So instead of optimize particular gamble pair on each trial, so we're going to just randomly just 2 out of 81, okay? And again, compare the performance, right? And then I have two simulations to show. One simulation, and data is going to come from weighted expected utility. And second one from expected utility. And I want to see how well the ADO would perform, meaning that identifying the underlying models. So that's the simulations, okay? And we ran this 50 stages, meaning that 50 pairs of gamble were presented. And okay, so let's start with this WEU. So simulation one, the data generating model is the WEU with these particular parameters. So that these are the actual coordinate of this corner. And you can see that even though this is, you can barely see it's a fan out, but it's almost parallel. So we create this situation where that even though data generating model is WEU, it could very well mimic that EU parallel, right? You want to see how well the ADO can discriminate, be able to say, well, that is WEU that's generating the data, okay? All right, so these are actual simulation trials. So we have stage of experiment, and which is actually number of gamble pairs from all the way to 50 gamble pairs. And then this is logarithmic scale. So this is a base factor in favor of weighted expect utility versus expect utility. So you can see that the log scales, they've been 10 to 0s. That means those two models, EU and WEU, they're equally likely. From the Bayesian model selection criterion, they're equally likely. And then the base factor here is 10 times. So that if that when you hit this boundary, say 10 times higher value than that one, that means that pretty much that one model is like determined to be clear winner, right? And of course, you can go all the way up to 100,000, right? So you can see that if you choose randomly on each of these stages without ADO, you can see that because the way you create those two models, especially data generating models, which are highly mimicking EU, we can see that. And there's no way that even after 50 pairs of gamble you present randomly, it's still undecided. You can't tell, right? There's no clear winner, right? Now, how that ADO does, that's like this, okay? So according to ADOs, if you're going to use this as threshold, with about 20 gamble pairs, the ADO quickly identified the underlying model is WEU pretty much. And this is that because this is log scale, this is exponentially goes. So this is the Bayesian term. This is positive probability of WEU being the data generating models. So you can see that this is where that if you're going to use, say, hard to recruit participant instead of running for 50 trials, say 1 hour, experiments can be done, say, 20 minutes, for example. And you still get the same quality data. But in this, actually, if you pick randomly, it may have to go hundreds of trials, right? And so since we're comparing between two, EU and WEU, while you're conducting experiment, computer in real time is updating primary estimate. So that for, so in this case, data come from weighted expected utilities, so that these are two parameters. That actually the data come from these values. One parameter is a 7 and 1.5. But initially, they are all equally likely. So we use the non-inferiority multiplier because we have no clue what the actual parameter values. The first stage is like that. And the expected utility, there's only one parameters, so they're all pretty much flat. Okay? So that's your start. You start from scratch. We have no clue which models, what parameter values. So after 16 stages, you can see that this posterior distribution massing around the two parameter values. And after 50, you pretty much pinpoint here. And of course, for EU, of course, if you estimate the parameter, update the EU parameters, it's also being narrowed down here. But of course, this is the wrong models. For EU, the best the EU can do, say that the slope will be somewhere between 0.1 and 0.2. Okay. So you get that. So what I'm going to show you the last few slides that what actually gamble pairs that ADO picked, okay? And so these are some of those gamble pair chosen ADO. So that, for example, that the one particular gamble pair was chosen, one trial was between these two, or that the low outcome is a 0, and then high outcome is 0.7, and the middle outcome, that should be like a 0.3, for example, all right? And there's another gamble pair. You can see that not every possible, there's about 81 the points here, but not every one those pair was chosen, because these are what ADO see as most discriminating patterns, okay? And it turns out that last 36 stages out of 50, it turns out that this ADO just pounding on these two pairs, that's one, okay? Because after the ADO has clear ideas that which models, but still some uncertainty about the parameter values, then you just looking for a sweet spot. It turns out ADO kind of pounding on these two pairs, so that these are the most discriminating patterns. And so, but this particular pattern, again, this is a fan-out patterns, okay? According to the WEU, is that it should choose that one. And then between these two, that should be chosen. But it turns out this particular pattern, which is ADO focused on last 36 trials, and no EU model can actually predict this particular choice patterns, all right? So this is what the ADO is sort of conversing on, all right? So this is a case was that EU cannot account for this particular choice pattern, but only consider with the WEU. So this is basically, you start with the huge uncertainty and just keep moving around and narrowing down the sweet spot. It could change over time. And then once they found this sweet spot, they'll just keep pounding on. Okay. So that was the simulation one. In the second simulation, let's switch the models. So now they come from EU. Okay. The EU has one parameter, which is like a slope. So this is the data generating EU models. Tom?
Shouldn't the arrival model be able to fit equally well if it puts its point of intersection far enough away?
Of course, that WEU with that point of intersection is infinite, that becomes just EU, right? So that if you move this point of intersection far away, then become more like EU, okay, yeah. In the limit, this become identical, right? Absolutely, all right. All right, so the same simulation, now in this case, data come from EU, and again, we have 50 trials. You can see that's again same base factor in favor of EU. So higher value means that posterior probability for EU is going to be higher. As you can see, if you just choose randomly after 50 pairs of gamble, no clear winner. Okay, again, because even though data come from EU parallel, but there's a WEU model could actually easily mimic that. All right, and that is the ADO trials. So compared to the first simulation, this was a bit harder, so that if you're going to hit this base factor 10, you need about 35 trials. The earlier was about 20 or 25 trials, because this is a bit harder okay? But you can see that if you just choose non-ideal fashion randomly, you may, again, need hundreds of trials. Right?
The jigsaw shape that's coming from averaging?
No, this is one particular trial. The reason why the fluctuation because that there's sampling errors, for example, because we have a model with that this probabilistic models. Even though one model predict EU, for example, predict choose gamble A or B, we assume that particular choice behavior is a stochastic variation. So this is a sort of sampling error. You get that. So this is one, not average one. Of course, if you average this hundreds of replication, you get a smooth curve. This is just one particular realization simulation. Okay, and all right. And these are the primary estimate. Again, the data come from EU. The value is 0.6. You can see that after about 50 stages, it completely narrowed down the primary values. Okay, initially it's completely uncertain. And then if you're looking for the corresponding WEU model, it turns out the primary value is over here. Okay, if you're trying to, these are the WEU model that could mimic that one, right? But by the time that EU has been identified as the data generating models. So this is how it works. And again, if you look at the particular gamble pairs were chosen, and these are the ones that was chosen by ADO in particular. And the last 28 stages of 50 trials, and then ADO kind of focused on these two pairs, right? These pairs. That means because these are the most discriminating patterns. With that, EU can predict trace pattern, but not WEU. Okay, same pattern, right? Okay, so those are two simulations. So, but these are simulations, not actually human experiment. But this was done some years ago. So since then also ran actual experiment, and with the human participant. So I just want to show you, this is a computer screen that what it looks like. So that this is actually a computer screen that experimenter would see. So there's a cubicle where the subjects are choosing, and that is the dotted red one. That's actually what the subjects see. So you present between two gamble A and B, and then which one would you choose? You knock on this, and then choose the second one, and then the experimenter sitting in the another room can actually see this. So while the subject is going from one trial to another trial, one state to another trial, we actually continually monitor. So given that, what's the likelihood now given that which models, which theories, you at the posterior model probability, and also the primary estimate. You can monitor online, okay? And then if you get one of those clear winners emerge, you can stop the experiment, okay? So just wanted to show you this. All right, so that comes to conclusion. And we think that ADO is a general purpose promising new experimental methodology that can be used for model selection, model discrimination, and primary estimation, as long as you have formal models, okay? And then we spend a lot of time trying to sort of speed up this, and so that this algorithm is a general purpose, so that if you had ideas about, I want to do experiments, say fMRI experiment, whatever, and we can quickly adapt our algorithm to your need. It can be, sometimes can be done a couple of weeks. So what we've been doing, and what you've seen today was that this is one application of ADO to judgment decision making. We also apply this to other domains. As mentioned earlier, it's visual psychophysics, developmental psychology, retention memory, and we also currently are working with the Air Force Research Lab, the domain of skill learning, okay? And also recently thinking about, or start doing, applying this fMRI, because that's what the money is, okay? And even clinical setting. That means take this out of the lab and then apply it to actual patients. Patient with some eye disease, whatever, heart disease. And those are two different ways of applying this idea. So different problem, different domains. But in terms of theoretical contribution or methodological contribution, and what you're seeing today is just standard ADO. But recently, we extend this to hierarchical-based ADO. So here's the idea. So that the AD using this, so this is, so for each individual, you just keep updating from the prior to posterior, just rotating around this. That's the AD you're seeing this, okay? So this is optimized for each individual. But turns out, when you do experiment, you not just have one subject. Subjects arrive in a sequence, okay? So it turns out you can also optimize the ADO over across different experimental participants. Because once you have, say, 100 participate, you know a lot about this subject's behavior, group behavior, because what you observe from one participant can actually tell us about what you're going to see in other patients. So that information, because even though there are individual differences, there are also individual commonality. So realize that we can also optimize across individuals. So you have another loop, so a super loop going on. For that, you need to build hierarchical Bayesian models because they capture the group behavior. They're allowing individual differences, but also focus on common properties. So another loop going on here, that's what I mean by hierarchical basis. Okay. So that while you conduct experiment for each participant, you have 100 subjects arriving every day. We also keep updating other loops going on here. So that's sort of learning aspect of ADO. And we had this paper currently under review, and that's was Mark Steiber sitting there, and he was involved in this. And we have not actually ran experiment human participant, but we have kind of algorithm is sort of set in place, so we're soon going to collect the data with the actual participant. Okay, so with that, well, thank you for your attention. Any questions?
There's lots of time for questions. We have about 15 minutes for questions.
I'll get to, but Don?
The late Richard Swanson often expressed the opinion that subjects were changing in the course of an experiment, and about the most number of trials you could get from a subject as he or she was changing was about 300, because over 300 trials, either the subject was learning or was getting fatigued. And so I don't know on what basis he came up with the number 300, but he didn't think he could.
It's a good question, but I always get that question. Because here, currently the way they set up assume that there's one models and one parameters throughout. So we assume stationarity, but it may not be, that's a realistic assumption to make. Maybe the subject behavior change, especially for early trials, subject trying to figure out what actually the task is about. So that what if that, there's some point that there's a changes occur, right? So that means the model has to be some sort of non-stationarity. You have to have a model built in such a way that it can detect the change. So this is a change detection. So at some point, well, maybe subjects has changed suddenly behavior, or this particular trial looks like a random. So that actually the current work we're doing. So we're trying to extend that. Maybe that's not stationary, maybe change from one model to another, even the parameters will change. How do you capture that while observing subject behavior? Computation hard problem, but can be done. So we have not done any simulation, but we're kind of looking at it too.
Well, I was going to say I thought it was good that you were discriminating between models and much less than 500 trials. Excuse me, 300 trials you're doing.
Well, of course, it depends upon not only the models, but particular parameter setting. Yeah.
The switching that
Yeah.
Don is talking about could be actually interpreted slightly differently. It could represent the uncertainty of the experimenter about which model is used. So instead of seeing the subject switching models, it's the opinion of the experimenter which may be switching depending on how the data is collected.
Well, I think kind of answering to that question, that one of the, again, assumption is that we have to assume that not only there's one models that generate data, but also even the set of a model has to be predetermined.
Yeah.
It has to be one of those.
Yeah, what I was really saying involved the idea that you combine the two models. In other words, you have one model which sometimes is this one and sometimes is this one. Right?
Now, you talk about the mixture model, for example. You maybe potentially maybe a dozen models instead of saying one. Say, well, actually the super model is some sort of mixture. You just adjust your mixture model. Yeah, we're also looking at that too. Yeah, because ultimately these are simplistic sort of demonstration, but in practice, actually, you have to assume these things can happen: non-stationarity, and you don't know which model, so then you may start with a large number of, say maybe you start with, say, 100 in theory, and then gradually narrow down. So that even the model set could change over time. Or even more, if you're ambitious, say, you do non-parametric base, which basically said the infinite number of potential models. We had looked into that, and it turns out computation is just intractable. So we gave up on that, unless the machine learning come up with the super fast algorithm. Okay, so this is some of this initial effort we're currently doing. But whole purpose is that we want to develop some general purpose could help you run the experiment, where that experiments can be very expensive, costly, and this could help you. But of course, it's not going to solve all your problem because it has assumption you have to make a limitation, computational. That's limitation. That's the most serious one we have to work on. Okay. Other question, Michael? You have questions?
Yes, there's a rival approach to this, which is testing theorems that are implied by one model but not the others. So that what you do is you instead of letting the computer do the thinking for you, you say, if this theory is true, then this theorem must follow, and then use the rival model to say where you should look for a violation of the theorem. I'm wondering if you could get your computer here to discover theorems that have been found out that discriminate these models.
Currently, that everything we do built on this the equation I shown you, and to the extent that you can formulate your ideas into that equation, okay, it can be done. So this one currently formulate that's the parameter priors, and then this is the likelihood function. So that even though you're doing axiom testing, somehow it can be turned that into different likelihood functions, and can be put into this framework.
But you're requiring to have functional forms specified, or either that or you have many parameters.
Well, you got to have the likelihood function should be functional parameters, but also design. So it has to have what you're going to manipulate. The design must be going into explicitly into your likelihood function. For example, certain designs. So if you do radical decision, you're manipulating, say, high frequency for the low frequency, but your model does not explicitly incorporate how the word frequency is the fact your likelihood function. Some of those design cannot be incorporated into part of the likelihood function. Then this method is not going to work. Okay, has to be that this has to be part of this likelihood function. So only the one that can be quantified explicitly. Okay.
You also made a decision early on. So I want to tease you about this.
Yeah.
This Marshak-Machina triangle is
Yeah.
also called the Bermuda Triangle of Decision Research.
I see. Okay, that's a great name.
Investigators go in there and they never come out of it. So many of the theorems that I've discovered that differentiate these fall outside that triangle. That's a good place to study EU, but it's not a good place to study the rivals to EU.
That's actually a very good point. Actually, Dan actually pointed out that to me. So that maybe EU, maybe you want those are sort of the gamma pairs in the borderline. But for other, if you discriminate between, say, rank dependent utility, which is a curved one, then you want to go into right in, then maybe you may not be able to never come out.
You get outside the triangle, because there's a lot left out by that triangle. So there are lots of three-branch gambles. This triangle is just a tiny little part of a much bigger space.
I agree.
You restrict yourself to gambles with 3 or fewer branches.
Absolutely. So as you can say, this is initial investigation, Dan. So now this is a Dan's work, and he's over Cal State University. So that's where his challenges, okay? And pick the gambles inside of this Bermuda Triangle, and also not just 3 outcome gambles, what about 5 outcome gambles? And what if not just 2? You want to discriminate between, say, 5 or 10 of those other theories, okay? And those are huge challenges, and that now is up to him. And, any other questions? Mark, yeah.
Maybe I shouldn't ask a question, but so model misspecification.
Yeah.
You talked a little bit about it.
Yeah.
So if the goal is discriminating between, let's say, 2 models,
Yeah.
and neither of the 2 models is correct, right? So the true data is generated by some other model. Is the choice of stimuli or experiments from EDO still the right ones for that task, or is it a good idea to occasionally throw in a random stimulus
Yeah, we also get this question. Another assumption you have to make that this models are correctly specified. But what if that actually data come from not just EU, WU, say rank dependent, okay? Then one question is that what would happen so then the optimal sort of stimuli would be choose toward which one, EU or WEU. In what sense that's optimal? Because none of those are actually data generating models. And again, we should also look at that too as one of my graduate students. That was a master's thesis. But ideally, it'd be nice to be able to prove theorems, what's going to happen. Okay, so maybe that ideal world tends to pick the models that's closer to data generating model in certain defined senses. But that was our intuition. But again, that kind of basically got nowhere. But that was one question. What was the second question you were asking?
Well, sometimes it's a good idea to do a completely random.
Oh, I see. So I see. That's a very good question, because in these cases, even here, fit these trials, every time you want to pick optimal best one, okay? Under the assumption that the data generating model is one of those two, okay? But that's probably not actually a realistic assumption to make. So then ideas, and maybe it's a good idea is that once in a while you throw in some non-ideal, okay, the random one. This is just almost like a simulated annealing, okay? So 90% of the time you go down the hills such a way that it would be the optimal, but once in a while just the random jitter, okay? And because that could be helpful, useful too. So maybe non-optimal ideal. Yeah, we thought about it actually, but we haven't done actual simulation. That's actually good ideas too. So the whole idea is that here's the ideal cases, but in practice, you have to do certain fine tunings or tricks, because the assumption we're making may not necessarily be realistic assumptions, but still want to be able to apply and get some benefits out of this. And these are all the practical concerns that we have to address when you take this out to outside of the laboratory to clinical settings, ultimately. These are all the good questions, and I usually get these questions. Any other question?
Since we have a lot of time, I have just a simple technical question about the discrimination between EU and WEU. I was wondering how your Bayes factor went up, showing that EU was better than a model that should be EU as well as EU, as long as you keep pushing that point further away. Is there some limit on how far away that point of intersection could be? So go back to the graph where EU was looking better and better.
Oh, I see. The second simulation talking about.
Yeah.
Yeah, right.
It was
So
a fixed point, wasn't it?
Yeah, were you restricting how far that intersection point could be? Yeah, this one. So
what do you mean? The intersection is here, basically. This is what up to that point, and even the ADO, because it exploring, but still that there's a WEU model it can mimic. So that so these are sort of what I can call this warming up trials. You have to pick about 25 of them. And after that, you have clear ideas. Until then, and because whatever you come up with the optimal, but there's a corresponding weighted EU model, so you cannot tell whether one is the better or higher Bayes factor than the others. But after this point, then you clears. Now it's a EU, and then the ADO keep pounding. Those one that.
It just seems to me, in principle, you must be restricting how far away that point of intersection can be, because it seems like the WEU model, in principle, should be.
Absolutely. So that, yeah. So that, for example, in this case, is that these are the range of parameters we pick, and then so WEU, those the converging point was a 10 up to 0 to 10 and 0 to 10. Okay. If you extend this further, of course, it takes a lot longer, because these are the primary range for the WEU, right? If you narrow down to say only these are the possible region, of course, then those breaking off point would be much earlier, right? Another question? Okay. Well, thank you.
Okay,
Thank you very
thank
much.
you.